Yeah, good morning, everybody. So this is the last day of this class. We want to talk about the inverter-based switched capacitor circuit. So we briefly talk about the inverter-based switched capacitor integrator in the preceding class. We will talk about the more details about the inverter-based integrator. Okay, those two are references. So the first part of this class will mostly talk about the reference number 1, and then the other part, the remaining part, will talk about the reference number 2. Okay. Yeah, for the number 1, yeah, before we talk about the inverter-based switched capacitor integrator, say we need to generate some supply voltage for inverters. So we wanna generate the supply voltage VDDP. So the peak current is some given current. So, in a supply voltage, see, I have an input voltage, and then I have a supply current here. Then I have some NMOS threshold voltage here. This is VDD prime, and this is VDD prime minus PMOS threshold voltage. Then the current waveform looks like that. Okay. We want to operate the transistor, inverter, at this operating point. So we want to set this supply current by using some additional circuit. Okay. So yeah, this is only logic threshold point, right? So I want to generate a bias circuit. See, I will use this bias circuit to generate this supply voltage by using some regulator. Okay, this kind of regulator. This is VDD prime, and then this is that generate the current I bias. Okay. So here, see, I just used a constant GM current source, but this is a rather new circuit because that resistance part is replaced by a switched capacitor. Yeah, I will copy this one. There, make it smaller. How come this thing doesn't change? Actually, this is not grouped. How come? This is not grouped. Oh yeah, it is grouped. All right. Okay. So if you look at this circuit, this is a constant GM bias circuit. Constant GM current source. See, only the resistance is replaced by this switch capacitor, a sort of switch capacitor. Say if this is by 1, now this is by 1 inverse. This is by 2 inverse, and this is by 2. Okay, so switched capacitor is a resistor in a macroscopic time scale. So we just redraw this circuit. Say I have this should be 1 to 1. Right? So I have 2 PMOS current source there, and then say, and then I have a NMOS current source there. Something like that, right? That's a constant GM current source. But see, we actually this PMOS diode is replaced by this one, by this differential amplifier. This is useful for low supply voltage circuits. We can reduce VDD even further by using differential amplifier. So let's redraw that part. Yeah, then so this connection just gain 1, right? So it should be positive this way, right? And then, yeah. Then say this works as a PMOS diode. Yeah, besides this drain source voltage of PMOS transistor become equal to each other, right? Because of negative feedback. So you see, there are 2 feedbacks here. One is a negative feedback through this loop, and the other is positive feedback through that loop, right? However, this negative feedback overrides this positive feedback because resistance looking downward is much larger than resistance looking at the left-hand side. So the loop gain of a negative feedback loop is larger than loop gain of a positive feedback loop. Okay. Okay, then see. You see, this is a 1 to 1. Drain source voltage is the same. This is better than this circuit, right? Because drain source voltage of PMOS is not equal to each other. The current may be slightly different due to the channel length modulation effect of PMOS transistor. However, in the right-hand circuit, drain source voltage are the same. Okay, no channel length modulation effect for PMOS. So this is 1 to n. Yeah, you can derive equations, current equation. Current should be the same, right? Current should be the same. Then, so gate source voltage of this one, gate source voltage is, if you recall, strong inversion current equation. Yeah, this VGS is this VGS plus IR drop, right? You can easily derive current equation. So this VGS should be on the left-hand side. This is VTH plus that current divided by mu Cox W of L. W of L is this one. this thing is N times W of L, right? So this is gate source voltage of left-hand side transistor, this M1. Yeah, gate source voltage of right-hand side transistor is, see, we assume VTH are the same. Yeah, the same current flows, right? Same current flows. Mu Cox W of L times N plus I times R, okay? That's a voltage drop across resistor R. So then, yeah, we just divide the square root I in both left and the right hand side terms. And then square root I we can derive, right? Which is square root I? My square root I will be, yeah, this 1 over R, or this thing, yeah, this is only square root 2I mu Cox W over L times 1 minus square root N, okay? Yeah, this will be my square root I. So I can derive, I can derive this I by squaring both sides of this equation, right? Yeah. So this is what? Yeah, in a strong inversion, my current should be mu Cox W over L R square twice 1 minus square root 1 over N square, right? So if N equal 2, if N equal 4, this I is only 2 mu Cox W over L R square, right? Yeah, in a switched capacitor, you know, those resistance is just a T over C, right? Sorry, the resistance is T over C. This is F clock times C, okay? So I can substitute this thing here. My current equation is what? Oh no, let's use this one, okay? Is this the one? Yeah, okay. Let's substitute my R there. Then what? This is R square, right? Yeah, then what's my GM? My GM of that transistor is 2 mu Cox W over L ID, right? Is this true? Oh, yeah. So I can substitute this thing, that thing. So my GM is 2. Oh yeah. So my GM is very predictable, right? It's determined by capacitance and clock frequency. Question? Nope. Okay. If this circuit works in a weak inversion, yeah, mostly inverters will be operated in a weak inversion. See, VDD prime will be determined something like threshold voltage of NMOS, threshold voltage of PMOS, plus 200 millivolt. So this is same as VGS-N plus VGS-P, right? At the logic threshold, at the logic threshold condition. So gate source voltage around 100 millivolt above threshold voltage, right? So it works at the weak inversion. Okay. So for the weak inversion, we can derive the current. Say this is a PMOS. So this is this is a positive, negative, and then what? Yeah. So this is MOS, and then this is R. Yeah. So this is 1 to N. Okay. Yeah. In this case, see, you can see this is some NVT log N. Okay. You will see that. So my current is only NVT log N divided by R, right? So in the service threshold, the GM is just I over MVT, right? Oh yeah, then it's easy. Say what's my this is log N, log N of R. If I substitute this R, this is FCLK C times log N. Okay. So again, it's a dependent on this clock frequency and C and log N. So my GM is very predictable. Even I can change my GM by changing clock frequency. Okay. Yeah, this is GM when the inverters work at that logic threshold point. Okay, logic threshold point. Question? Nope. Okay. So let's continue with the see. This is I bias. That I bias is generated by this circuit. See, it has a filter, ripple filter there, low pass filter, right? Ripple filter. A low pass filter eliminate that switching transient. So this becomes a DC voltage. So it generates I bias, which is proportional to those current, right? Now see, I can even multiply this by M, 1 M. Then I can even adjust the GM. Okay. Yeah, if this is M, say this is multiplied by M. In the previous case, it will be multiplied by square root M or something like that. Yeah. Here, this GM should be multiplied by square root M, something like that. Okay, so see, this is say, this is my inverter. For example, this is W over is 1 by 1, 3 by 1, or something like that. Okay, I want to generate this supply voltage for inverters, so I will supply this one to all inverters in the circuit. Okay. This VDD prime is distributed to all inverters. Yeah, so say if I make this one 1 by 1, so this is a diode, right? Then the situation is the same as this inverter operating at the logic threshold point, right? Logic threshold. At the logic threshold, this input voltage is same as output voltage. So, situation is here. Gate voltage is same as drain voltage. So, if I make this voltage, this voltage, say V1, to be same as that voltage here, and also that voltage there, or by using this negative feedback loop here. Then, see, this VDDP will be, by this VDDP, this transistor will be operating at the logic threshold point, right? Because diode. At the logic threshold point, it's just something like that. So I just generate this voltage and then making the same here, right? Oh, let's just see. Oh, sorry, one thing is missing. Oh, should be there. There should be connection there, okay? Connection, okay. I need to connect this gate and drain, input and output of inverter. So this part is the same as that part, right? This voltage is the same as, if this voltage is set to same as that voltage, okay? Then this voltage drop corresponds to, the PMOS drop at the logic threshold, all right? Yeah, usually this is called LDO, low dropout regulator. This is a voltage regulator, right? So I have do I have reference voltage? Yeah, this is my reference voltage. From reference voltage V1, it generates a supply voltage VDDP. Usually this part is just a resistor, right? This part is a resistor. See, R1, R2, then my VDDP will be R2, R1 plus R2 times V1, right? That's a conventional LDO circuit. But here, those two resistors are replaced by NMOS diode and PMOS diode in series, okay? Yeah, this is a differential amplifier. And then those are source follow circuits. So forget about this part, digital part. See, this gains, AC gain +1. So you can see this source follow can supply large current, okay? Yeah, this is actually a source follow circuit. So, this is VC, which is this voltage VC. And then this is a VDD prime. This is a PMOS source follower. This may be VDD, and this is a VDDP. This is called the pass transistor. Okay? All right. So this voltage will be distributed all the supply voltage of all inverters in a circuit. Now, all inverters, the supply voltage will be this VDDP. Okay? Then the current at the logic threshold point is the same as I bias, right? That I bias. Question? Nope. All right. So yeah, so we just start with okay. No.